time here. Okay, and so we finished up this question last time. We're going to move on now to talking about, instead of strong acids and strong bases, which are relatively simple to figure out the hydronium and hydroxide concentrations because there's no equilibrium, we'll now deal with weak acids and weak bases which do have an equilibrium. So we'll have to do an equilibrium calculation with an ice table and all of that. So let's get started with those. So if we have a generic weak acid, so the weak acid here is, we'll call it HA. That's a very common way to just call a generic weak acid. It has the H plus ion and then some anion, which we call A minus. And so when the weak acid acts like an acid, it will give the proton over to the water. And then the water has 3 H's and the charge is +1. Because remember, when a proton is grabbed, you don't just get H, you get H plus. So the H's go up to 3 and the charge goes up by 1 unit from 0 up to +1. And then the H plus was lost from here. And so we lose the H, it's no longer attached to the anion. And we lost H plus, so the electron is left behind, meaning the charge goes down by 1 unit from 0 down to -1, and these are our products. Now, if we wanted to write a K for this reaction, well, we would include the products over the reactants. We won't include water because it's in the liquid state, not the aqueous. We only include aqueous and gases in Ks. So products here will be on top. We'll have the concentration of H3O plus to the first power times the concentration of A minus to the first power. And we're going to divide that by the reactants, the concentration of HA, also to the first power for this reaction. And so you can see that this K, which we call Ka for an acid, is the same as any other K. It's the product concentrations to their powers of their coefficients divided by the reactant concentrations. It's really no different. It's just we give it a special name. We say this is the Ka or HA, which means it's the K, the equilibrium constant, for this particular reaction where HA is acting like an acid and giving its proton to water. So at that point, if we have the Ka, we can solve for these concentrations in basically the exact same way that we did in chapter 17 for any equilibrium calculations that we did. So let's see an example of that. Before we do, rather, here are some Kas for a variety of different strong and weak acids. So here's a strong acid, HCl. Its Ka is very huge. Remember, a big K means you get a lot of products. So the HCl, it completely dissociates in water. Of course, it produces a lot of product, H plus and chloride ion. So its Ka is very big. The bigger the Ka, the more dissociation will happen, meaning the stronger the acid is. So you can see HCl is very strong, very big Ka. HNO2 is pretty strong. HF is also pretty strong, even though they're not considered strong acids. They're on the stronger side of weak acids. Methanol, for example, is a very, very weak acid, or HCN. Its Ka is very low. Now, something you'll also see is a so-called pKa. So just like a pH is the negative log of the hydronium concentration, or the pOH is the negative log of the hydroxide concentration, the pKa is the negative log of the Ka. So we could calculate those from the Ka. So if we have the, right here, let's say we want to get the pKa of HNO2, we would do 4.5 times 10 to the -4. We'd take the log of that, and then we'd change the sign with a negative, and we get 3.35, which is the pKa. So pKa's you'll see a lot in your biology classes and organic chemistry classes. They often write the Ka's in pKa's instead. And you can see the bigger the Ka, the stronger the acid. Or on the other side, the smaller the pKa, the stronger the acid. And here's a reminder of that equation. pKa is the negative log of Ka. So let's actually use the Ka now. let's say at this point, we're going to have, remember, there were two types of questions when we were doing equilibrium problems. One of them was where we were given the equilibrium concentrations and asked to determine the K, the equilibrium constant, from those equilibrium concentrations. The other type of question was where we were given the Ka and asked to determine the equilibrium concentrations. Now, the first type, which this one is, where we're trying to find the Ka and we're given the equilibrium concentrations, this is the easier type, okay? So here, you may not recognize right away that we have been given the equilibrium concentrations. It may not be apparent, but the way the equilibrium concentration was given here was by giving the pH, because the pH will tell us the hydronium concentration, or we can get the hydronium concentration from that. And that is the equilibrium hydronium concentration. So then we can get all the other concentrations. Now, the reaction here is HF. So our weak acid is HF, and it's going to be in water. So that's what we'll write first, HF here in water. And it's going to be behaving like an acid. So there will be an equilibrium here. And the H plus will be given to the water. So we'll get hydronium ion, H3O plus. Also, what's left behind, the conjugate base of the HF after it loses the H plus, is F minus. See, it is one less H, and the charge is down by 1 unit. So even though we don't need to make an ice table for this type of problem, because we're not asked to solve for X and find equilibrium concentrations, it's still sometimes useful to do the stoichiometry in an equilibrium, in an ice table. So I'll just do the stoichiometry here in an ice table. What we do know is we're starting here with 0.25 molar HF. So that's what will go right here, 0.250 molar. This is molarities, even though I didn't write them. And we're going to say that we start with about 0 H3O plus. Now, realistically, in pure water, there's always a little bit of H3O plus. It's 1 times 10 to the minus 7 molar. But we're going to assume that that is so small that we can ignore it. We should always think about whether that is true or not. We'll see. And there is no fluoride ion to start in the solution. So, of course, now we could calculate Q. Q would be 0 since these are 0 or close to 0. So the reaction, Q would be less than K. The reaction has to go forward. You could probably figure this out just by inspecting the reaction. You can see here that there's no product, so the reaction can only go forward. So that means this here, we're going to put a minus X, minus 1X, since there's a 1 here. And then over here, we'll put plus X and plus X. For water, we don't put anything. It doesn't affect the equilibrium, so we don't have to put anything about the water. So our equilibrium concentration of HF will be 0.250 minus X, and for H3O plus and F minus, it will be X. Now, the thing is, we know what the equilibrium concentration of H3O plus is, or we can find it because we have the pH at equilibrium. So to get the H3O plus concentration, we do the antilog of the negative pH. So let's do that real quick. We have the pH is 2.036. We'll take the negative of that, and then we'll do the antilog, which looks like this button here. And that gives us 0.00920. And because the pH was written with 3 after the decimal, we will write our result with 3 sig figs, the 9, the 2, and the 0. And that is our X. That is our concentration of hydronium at equilibrium. So we can plug these in here. The only one we have to find is the 0.250 minus X. So let's find out what that is. So in terms of Ka, because we have this reaction, it's going to be hydronium and fluoride on the top, each to the first power. And it's going to be HF on the bottom. And we figured out hydronium and fluoride already. It was X. So it was 0.00920. What we have to do is figure out HF. HF was 0.250 minus X. So the X was 0.00920. And so we subtract, let's subtract that, 0.250 minus 0.0092, and we get 0.2408. Now, when we're subtracting, we look at the place value. Since the 0.250 has the fewest place values, only to the third, we have to round to where the third is. Since this is an 8, we'll round the 0 up, and we get a 1. And now we can plug each of these in. We'll plug 0.00290 in for H real plus and for F minus. And then we'll plug in 0.241 into HF, and that will allow us to get the Ka. So we plug those in, 0.00920 for each of these here, and 0.241 will go down here for HF. And now it's just a matter of calculating. We've got 0.00920 squared divide by 0.241. And what comes out of our calculator is this. And we would want to have it to 3 sig figs, since each of the things we were multiplying and dividing had 3 sig figs. So we'll write 3.51 times 10 to the 4th. And that will be our Ka. So again, this was a question where we were given the equilibrium concentration and asked to find the Ka. So we didn't have to solve for X, solve the quadratic or anything like that. We just had to figure out figure out all the concentrations and plug them in. We were given the equilibrium concentration. What makes these a little bit trickier is they don't say this is the equilibrium concentration in these problems. They just say the pH of the solution is this. And you're supposed to infer, well, oh, that means that at equilibrium, the hydronium concentration is, can be found from the pH. So that's
sorry.
Yes, question.
But every time they do the pH, that's basically equilibrium?
Yes, so here, going back to the question, it is a little bit tricky the way it's worded, but a chemist would understand it, but you guys are becoming chemists or scientists. The wording is a little tricky with these, and that's why I mentioned it a little bit. So the concentration of HF, the weak acid, when you first put it in, is 0.250. But that's not the concentration of H+. So what they do is they give you the pH of the solution. That's how you can figure out the concentration of H+. And you kind of have to kind of do a few of these before you understand why they say it that way. It's because here we know that the hydronium concentration is very small before any of this HF dissociates. So clearly the pH can't be 2.036. It's not 2.036 in pure water. So that can't be the initial concentration. It must be indicating at equilibrium, even though it's not said explicitly. And this is very, very common wording for this type of question. Other questions about this one? Okay, so this was like in chapter 17, except it was just for acids, and it was the kind of question where we've had to find the Ka. We weren't given it. Oh, and then they asked also for the pKa. The pKa is the negative log of the Ka. So negative log of this Ka right here. So we would put 3.51 and EE minus 4. We take the log of that and then we change the sign because it's negative log. And we get this number. And of course, we're doing a log of a number with 3 sig figs. So it should be, the answer should be written with 3 after the decimal. So we would write a pKa of 3.455 because this is a 6. So we'd round the 4 up. So that's how you do a problem where you get the Ka or the pKa. What about the other kind of problem, the harder kind of equilibrium problem we did in the last chapter? It's where you have to figure out the equilibrium concentrations. So in this chapter, again, the wording will be a little bit different. It will say calculate the pH. And the pH here is what we say to talk about, what is the equilibrium concentration of hydronium? That's what we're really trying to find to get the pH of the solution. So we're going to have to make an ice table and solve for X because we're given the Ka and we're being asked for equilibrium concentration of hydronium so that we can get the pH. So the question will look like this: calculate the pH of a 0.1 molar HCN solution. And they say at 25 degrees Celsius, Ka of HCN is 4.9 times 10 to the minus 10. So we should write down the equation. We have the weak acid HCN. We're going to want to write that with water on the left side. So HCN aqueous plus water. This is a weak acid. It's not one of our 6 strong acids, so there will be an equilibrium. We can also tell it's a weak acid because of Ka. All right. And the result is going to be the HCN giving its proton to water. It's acting like an acid. So the H plus comes off of the Cn minus, it goes to the H2O, so you get 3 H's. Also, the charge goes up by 1 unit from 0 up to positive 1. The H plus is being lost from the cyanide, so you can see there's no more H here, and also it's lost H plus, so the charge goes down by 1 unit from 0 down to negative 1. And since this is an equilibrium problem where we have to solve for X, we do have to set up an ice table. We've got the initial concentration of the weak acid HCN. It's 0.1 molar, so we're going to put that right there. And again, we're going to assume that the H3O plus is about 0. We do know it's actually 1 times 10 to the minus 7 in pure water. However, we're going to assume that's small enough that it doesn't affect our result. So we're going to say it's very close to 0. And the cyanide, we have none to start with. Okay. And so now we're going to, again, decide whether the reaction is going forward or backwards. Here, Q is 0 again, less than K. It must go forward because there are no products to make it go backwards. It has to go forwards and make products. So we're going to have minus X here, minus 1X. We're going to have plus X here and plus X here. Okay, and so our equilibrium concentration of HCN will be 0.1 minus X. It will be X for H3O plus and X for Cn minus. Now let's write the Ka for this reaction, the Ka expression. So the Ka here is going to be equal to products over reactants. It's the K for this reaction, HCN acting like an acid. So the products will be H3O plus on the top and Cn minus. Those will each be to the first power. On the bottom will be HCN, also to the first power. One nice thing about these acid calculations is most of the time everything's to the first power, which makes things a lot easier than some of the other questions that we had done in the previous chapter. But it's still written the same way. Just K is products over reactants. It's just this K is specifically for HCN acting like an acid and giving a proton to water. So now plugging in, we're going to have X for H3O plus and X for Cn minus. So we're going to plug in now. We're going to plug in X for H3O plus and X for Cn minus. And for HCN, we're going to do 0.1 minus X. And this is equal to the Ka we were given, 4.9 times 10 to the minus 10. Now, this is where it's probably going to be useful to use our simplifying assumption here, because we can't just take the square root of both sides. You can't take the square root of this easily. And so we're going to want to hopefully assume that 0.1 minus X is about the same as 0.1. So let's do our pre-check. So our pre-check is we take this value, the initial concentration, we divide by the K, right here, and we check, is this greater than 400? Yes, yes it is. So our pre-check checks out. So now we can say x is going to be very small. So 0.1 minus x will be about the same as 0.1. And we'll multiply here x times x, so that's x squared. So now to solve this, we need to multiply both sides times 0.1. That will cancel this 0.1 here. And that will get us, let me do this step by step. So let's multiply 0.1 times 4.9 times 10 to the minus 10. You should be able to do this in your head. If we multiply this, whoops, what happened there? 4.9 times 10 to the minus 10. Oh, God. 4.9. Okay, 4.9 times 10 minus 10 times 0.1. So that gives us 4.9 times 10 to the minus 11. Then we need to take the square root of both sides to get x. So we take this to the 1/2 power, that's taking the square root, and we get 7.0 times 10 to the minus 6. So that is the x, and that is the concentration of hydronium. So now to get the pH, we just need to take the negative log of the concentration of hydronium. So we do that. And so negative log of 7.0 times 10 to the minus 6. Let's do that. And the calculator too. Where did the calculator go? Okay, so we have 7.0 times 10 to the minus 6. We're going to take the log of that and reverse the sign. Oops, log of that and reverse the sign. And we get 5.15. Again, because we're logging a number with two significant figures in it, we're going to write the answer to the log with 2 after the decimal, 5.15. So the pH of this solution is 5.15. Okay, so anyone want me to repeat a step there? Go back a little bit.
Yes, can you repeat the part where you did the x equals hydronium? I just need to see, I input the 4.9 times 10 to negative 10 power in the calculator.
Okay, and so we had 4.9. So we're going to multiply both sides by 0.1 here. Let me write on the slide here. Annotate. So we're going to multiply both sides by 0.1. And this will cancel right here. And we'll multiply here, 0.1. And so let's do that in the calculator. 4.9 times 10 to the minus 10. And then that's going to be times 0.1. So we get 4.9 times 10 to the minus 11. And this is going to be equal now to x squared. And now what we want to do is take the square root of both sides. So then we'll get x equals something. So x equals the square root of this. So we'll take, my calculator doesn't have a square root button, so I have to do to the 1/2 power, which is the same as square root. And that gets me x equals 7 times 10 to the minus 6. Questions there?
Okay, thank you.
Mm-hmm. Yeah, I kind of skipped a step there, sorry. Other questions? We should probably also do a post check. Is this number less than 5% of 0.1? I think you can probably tell, yeah, it's about you know, almost, it's about 100,000 times smaller than this almost. So yes, it's much smaller. So our you know, our assumption here that x is small and 0.1 minus x is about the same as 0.1, it was safe. And we're going to be using the simplifying assumption a lot. That's going to be the primary way. You won't have a lot of situations where you've got to solve the quadratic, but make sure that you are good with the simplifying assumption. That's going to help you a lot in this chapter and the next one. So in general, our process is not all that much different than any of the equilibrium calculations we did in chapter 17. First, we have to recognize what our acid or base are. So that's something new because specifically we're dealing with acid and base. We have to write the balanced equation. So that's what we did in each of these problems. We wrote the equation for the acid behaving like an acid. And then you got to so you're going to identify the reaction and you're going to make your ice table. Then you substitute in the equilibrium concentrations written in terms of X, solve for X, calculate the concentrations, and calculate all the remaining concentrations. Usually you're interested in the pH. So once you get the hydronium concentration, you just take the negative log of that and you're done. But you could, of course, figure out the concentration of anything else as well. Just usually what you're asked for is the pH in these problems. So what about when you have acids of varying concentrations? So another way to describe an acid is by the percent that it dissociates. So we said that for strong acids, they have 100% dissociation, but weak acids do not have 100% dissociation. In fact, their percentage dissociation will depend on how much you started with. I'll show you why that's true. So the equilibrium constant is always the same, but the percent that the weak acid will dissociate depends on what you start with. And this is another way. I don't really talk too much about this. I just give an example here, but usually, you know, it's best to express how acidic something is in terms of Ka, because it will always be the same no matter how much of the weak acid you start with. But percent dissociation is another way. So this would be the percent of the weak acid that dissociated divided by the initial amount of weak acid that you started with times 100%. So let's say we have acetic acid. So this AC is meant to represent the acetate ion. It's just shorthand to make this writable a little bit easier. The Ka for acetic acid is 1 times 10 to the minus 5. So let's say let's start with this situation right here. So if we start with 1 molar of acetic acid, and I'm just going to give you the data here like we were doing an experiment. We started 1 molar of acetic acid. 0.42% of that is going to be 0.42%. 0.42% means 0.42% per 100. So that in terms of a decimal is 4.2 times 10 to the minus 3. If we multiply that times 1 molar, we get that the molarity of the acid that dissociated was 0.0042. So this would be the HA dissociated. Okay, and so that means that we would get 0.0042 molars of the hydronium and 0.0042 molars of the acetate. The amount of acid that you really originally started with was 1 molar, and so the amount that dissociated is very small compared to that. So let's say we put now all of this into the Ka. So we had that since this was 0.42% dissociated, there was 0.0042 molar of the H3O plus and 0.0042 molar of the acetate ion. And the remaining amount of the acetic acid was the 1 molar we started with minus the 0.0042 molars that was used up. If we calculate this, we would find what the Ka is, so I'm plugging it into the Ka expression so we could calculate Ka and confirm that it is in fact, so 0.0042, that would be squared, divide by the quantity 1 minus 0.0042, close the parentheses, and equals. And so we get about 1.8 times 10 to the minus 5. So indeed, if it's 1 molar, we have confirmed that the acid would 0.42% dissociate that. We've confirmed that because when we plugged in the resulting concentrations, we got the same Ka. Now let's say instead, we're starting with a smaller amount of dissolved acetic acid. Let's say instead, we're starting with 0.01 molar acetic acid. It turns out that if we were to observe the dissociation, we would find that 4.2% dissociated. So the concentration here of the acid that dissociated, the amount of acid that dissociated would be 4.2%. We're going to turn that into a decimal per 100. That's 0.042. And then we're going to multiply that by what we started with times 0.01. And so our concentration here of the acid that dissociated would be 0.0042. So what that means is that we would produce 0.00042 molars of H3O plus, 0.0042 molars of acetate ion, and our remaining amount of the acetic acid would be 0.01 that we started with, minus the 0.0042 that were used up. And so if we plug those into the Ka expression, we get 0.00042 on the top, 0.00042 on the top as well for the H2O plus and the AC minus. And for the acetic acid is the 0.01 minus 0.00042. Let's confirm that that gives us the exact same equilibrium constant. So 0.00042 squared divided by 0.01 minus 0.00042, close the parentheses, equals. And we get 1.8 times 10 to the minus 5, meaning that here what you can see is that although the percentage of dissociation changes depending on the initial concentration, the Ka is always the same no matter how much you start with. And so that's why I think Ka is a better measurement of how strong an acid is relative to percent dissociation, because it does not depend on how much of the acid you started with. The percent dissociation does. And so, yeah, you can see though, basically what happens is that we can see that the difference between 1 molar and 0.01 molar is 100 times. So when you change the concentration and make it 100 times less, you get 10 times more dissociation. And that's the relationship between them. It's because it's essentially 10 squared. But again, you should know what percent dissociation means, but usually what we're working with here is Kas. But I wanted to show you that although the percent dissociation will change depending on how much of the weak acid you have dissolved, the Ka is the same no matter how much of the weak acid you start with. Questions about the percent dissociation? So if you're ever asked to calculate the percent dissociation, this is what it means right here. So for example, let's say the second case, our amount that dissociated was 0.00042 molars. And the amount we started with, so the HA initial was 0.01 molars. So that gives us a decimal, and to make it a percent, we multiply times 100%. And so we can see that it was, I just did this calculation backwards. It was 4.2% dissociated. The amount that dissociated was this, that was up here, right here. The amount that dissociated was, whoa, this right here, that was up here. The amount we started with was 0.01, that's down here, times 100%. That is 4.2% dissociated. Okay. So what about polyprotic acids? So for polyprotic acids, these are acids that have more than one proton that they could give. Now, generally on exams, I don't have you calculate the pH of polyprotic acid. It's just the problems are too long. But I do like to show you one example, and we do one titration on Wednesday of a polyprotic acid. So an example of a polyprotic acid would be carbonic acid. It has 2 protons on it that it could lose. So here's the equation where it loses the first proton. So the H plus moves over here to the H2O. We get 3 hydrogens, and the charge goes up by 1 unit. The H plus is lost from the acid here. So now in the conjugate base, there's only 1 H. And we've lost H plus, so the charge goes down by 1 unit from 0 down to -1. So when it comes to polyprotic acids, they actually have 2 Ks to them. So there's the first K, which is the K for the reaction where the first proton was lost. So that would, again, just be products over reactants. So the Ka1 for carbonic acid, when it loses its first proton, would be written with the expression of H3O3 plus on top and bicarbonate ion also on top, both to the first power. Then on the bottom, we won't put water again, but we will put the carbonic acid here. That's the reactant, also to the first power. But with polyprotic acids, this bicarbonate ion could also potentially lose a proton. Okay, so we can see that the Ka1 here we're given is 4.3 times 10 minus 7. But this bicarbonate ion could also lose a proton. So if we write this acting like an acid, we'd copy it down here with water. So now we have the carbonic acid, but it's the bicarbonate here losing the second proton. And so again, the H plus is being transferred over to the water. So the water is now H3, 3 H's, and the charge goes up by 1 unit from 0 up to +1. And the bicarbonate has now lost the H, so there's no more H here in the conjugate base. Also, the charge goes down by 1 unit from -1 down to -2. And so the K for this reaction would be called Ka2 for carbonic acid. It's the K when it loses a second proton. Ka2 is the K for this reaction right here. So Ka1 is the K for this reaction, Ka1 of carbonic acid. Ka2 for carbonic acid is the K for this reaction. So the K is written the same way, though, as anything else. Once you know the reaction, it's pretty easy to write the K. You just put the products over the reactants. So product H3O plus concentration to the first power, carbonate concentration to the first power. Those are on the top. On the bottom, we have bicarbonate concentration also to the first power. And so you get the K for this. The Ka2 for this one happens to be 5.6 times 10 to the minus 11. And one thing you'll notice is that in general, the Ka1 is much bigger than the Ka2. Of course, because it's much easier for the first proton to come off. The H plus comes off, you get bicarbonate ion. Why do you think it would be much harder to remove a second H plus? What about this will make it hard for the second H plus to come off? the H plus will be attracted to this. Why? Look right here. Bicarbonate is negative, right? Carbonic acid was neutral acid, but after it loses its first proton, now it's made a negative. Yeah, it's already negative. It's negative. Diego's got it. Yeah, it's negative. So it's attracted to H plus ions, and it's not going to as easily give them up. And you can see that here with the K. The Ka2 is much bigger, or much smaller rather, because it's much harder for the second H plus to come off. So in general, it's the first equilibrium that will contribute the vast majority of protons. The second one is generally almost negligible. You can see that the H3O plus produced by this reaction is 1,000 times less than from the first one. And so it's not really going to make much of an impact, the second one. So here are some Kas for a variety of different diprotic acids. We can see here carbonic acid as Ka1, Ka2, hydrogen sulfide or hydrosulfuric acid, Ka1, Ka2 is super small for that one. Sulfuric acid, you can see the Ka1 is very large. That's because sulfuric acid is a strong acid. So the first proton comes off quite easily. Even the second one isn't too hard to take off. It has a relatively high Ka. Notice that phosphoric acid even has a Ka3. This is because it has 3 protons that it can lose. So the first Ka is the K for the loss of the first proton, K for the loss of the second proton, K for the loss of the third proton. And so we can see again, looking at the Ks, the Ka2 is generally much smaller than the Ka1 because taking off the second proton is a lot harder. It's harder to pull off something positive from something that's already negative. So here's an example of how to do this. I think it's a good example of another equilibrium, solve for equilibrium problem. And I'll prove to you here that you can essentially figure out the pH of this solution based on the Ka1. We're going to also include the Ka2, but what we'll find is that it does not affect the pH significantly. So we're going to write down the equation for this as a weak acid. So it's going to be carbonic acid and water. And the carbonic acid is going to give the proton to water. We get H3O plus and we get bicarbonate ion, just like we wrote on the last slide. Okay, so we write an ice table. The initial concentration here, 0.2 molar for carbonic acid, about 0 for the hydronium and 0 for the bicarbonate. And of course, this has to go forward since there are no products. Q is 0, which is less than K. So we'll put a minus X here, a plus X here, a plus X here. So our equilibrium concentration of carbonic acid is 0.20 minus X. And for these guys, it's X and X. And so now we write the Ka expression. So these guys on top, both to the first power. And then on the bottom is the carbonic acid, also to the first power. No water, since it's not aqueous. And now we plug in the concentrations. So on the top, we're going to have X and X. Here, X and X. And the bottom will have 0.20 minus X right here. Okay. And again, we're going to hope to be using our simplifying assumption. Otherwise, the math is hard. K is pretty small, so I think we're going to get to use it. Let's copy this over now to the next slide. And by the way, this is all going to equal 4.3 times 10 to the minus 7. That's the K that's given. Okay, so we copy this over. 4.3 times 10 to the minus 7 is X squared over 0.2 minus X. We want to do our pre-check now to see, can we do this? Can we go ahead and say 0.020 minus x is about the same as x. Remember, we take our concentration here and make sure it's at least 400 times bigger than the k. We want the k to be small. That means x will be small. So 0.02 divide by 4.3 e minus 7. It's 46,511, which is way bigger than 400. So we're good on our pre-check. We can go ahead and assume here that 0.2 minus x will be about the same as 0.2. So that's what we're going to assume here. 0.02 minus x is about the same as 0.2, and we'll call this x squared. And this is equal to 4.3 times 10 to the minus 7. So now let's multiply both sides by 0.20. So I'm going to annotate this again. So we're going to write 0.020 and multiply that, so that cancels, and 0.020 right here. So let's multiply that now on our calculator. 0.020 times 4.3 e minus 7. Okay, and that will be, so that will be equal to x squared. It's 8.6 times 10 to the minus 9 equals x squared. So now we're going to take the square root of both sides like that. So I'm going to put this to the power of 1/2, which is taking the square root, and I get 9.27, or 9.3, I suppose, to 2 sig figs times 10 to the minus 5. And so that's what I'll write here now on my slides, 9.3 times 10 to the minus 5 molar. So that is our concentration of hydronium from the first equilibrium. Okay. Now let's deal with the second equilibrium. Oh yeah, and let's get carbonic acid. That will be 0.2 minus x. So 0.2 times minus 9.3 times 10 to the minus 5. It's about the same as 0.02 because this x is just so small, but that's what we expected, right? So we're just going to write this to 2 sig figs as 0.2. All right. And so now let's continue. Any questions before I continue here?
Are we always going to have to look for the two Ks?
The 2 Ks? As I said, I don't tend to focus on calculating the pH of a diprotic. However, it's important to understand the concept. So I'm doing one calculation and kind of explaining the concept, but you should note, yeah, if a acid is diprotic. What I'm going to show you here, though, is that for a diprotic acid, generally it's only the first equilibrium that affects the pH. The second one, you can ignore it. And that's what I want to prove to you right now with this calculation. But we're not done yet because we only did the first equilibrium. Now we have to do the equilibrium for the bicarbonate ion losing its proton, and we can see how much that contributes to the H3O plus concentration. So, oh yeah, post check here. Did a post check. Is this less than 5%? Yes, it's definitely way less than 5% of our original amount. We can see here when we subtract them, it basically makes no difference. So now, let's clear our drawings here. And now we have to deal with the second proton that carbonic acid can lose. This HCO3 now can lose a second proton.
Can you go back to the last slide very fast?
Sure.
Okay. I just needed to see the post check. Thank you.
Oh, yeah, sure. So we take the the X and we compare it to what it's subtracting it from and making sure it's less than 5% of that. So now we're going to have to carry forward this concentration of hydronium and bicarbonate ion. We're going to carry that forward into the next slide. So note that, because now we're dealing with bicarbonate ion losing a proton. So this H plus will go over to the water. It will make H3O plus, and the conjugate base, once this has lost the H, it will have no H, and also the charge will be one less since it lost H plus, goes down from -1 down to -2. So in terms of this ice table, we've copied down here what we got from the first step, the bicarbonate concentration and the hydronium concentration. We don't have 0 of these. That's how much we had from the last step. We do have no carbonate. None of that has been made yet. And again, Q would be 0 because the carbonate is 0. If we'd had 0 times this divided by this. So Q is 0. This reaction has to go forward because it can't go backwards since there's no carbonate to react and make it go backwards. So then we'll have minus X here, plus X here, plus X here, all 1X because these are all 1 right here. And so we'll have 9.3 times 10 minus 5 minus X, 9.3 times 10 minus 5 plus X, and X. So we're going to write the Ka expression. Notice here that Ka2 is much, much less than this initial concentration. Again, this is like doing our pre-check here. Let's do our pre-check. If we compare our initial concentration, 9.3 times 10 to the minus 5, and we divide that by the K, which is now for this one, for this Ka2, 5.6 times 10 to the minus 11, we get that that is far greater than 400. It's like 1,000,000. So we can see that X is going to be very, very small. So we can assume that 9.3 times 10 minus 5 minus X and 9.3 times 10 minus 5 plus X, the X doesn't really change the number very much. And so this is what ends up happening when we go to calculate it. We write the expression for the Ka2. It is these products here, hydronium and carbonate, over the reactant right here. So these products here over this reactant right here. Okay. And we then plug it in. So we put 9.3 times 10 minus 5 plus X here, X for the carbonate, and 9.3 times 10 minus 5 minus X for the bicarbonate. We use our simplifying assumption saying that minus X here, the X can be ignored, it's so small. Plus X, the X can be ignored, it's so small. And then these are going to cancel here. So we get that X equals to the Ka2. And X is the concentration of the carbonate. And so that would be 5.6 times 10 minus 11. But notice that when we add this to the hydronium concentration, it doesn't really affect it at all. So what we figured out in the first step, that was all, basically almost all the hydronium that was going to be made. So we can just now calculate the pH based off of that. So the pH is going to be the negative log of 9.3 times 10 minus 5 plus this, but this is so small, it makes no difference. So it's going to be the negative log of what we got in the first step. So 9.3 E minus 5, log it, change the sign. We get 4.03 with 2 after the decimal, since this had 2 sig figs right here. So notice that in the case of diprotic acids, really all of the hydronium is coming from the first equilibrium. Very, very little is coming from the second. It's really a negligible amount. When we add it to, when we add this to this, it doesn't change the value of it at all, really. So again, I don't put these on exams. Diprotic acid, I think I put 1 in your homework because they're so long. But I did want to demonstrate to you how it could be done, and the fact that even if you were doing one, like if you were doing one on a multiple choice exam, which I had one back in at UCR, the way I did it was I just figured out the first equilibrium and said, forget the second equilibrium. I know it's not going to do anything to the pH. And that because I had to do it on a very short-term time exam, that helped me out a lot to know that. But you should just generally be aware of that idea of how diprotic acids separate. And you should be able to write the equations in this fashion. So anyone want to ask a question about that one there? Okay. All right. So now we've done a couple of acids. So we did a weak acid and we did a weak acid that was diprotic. Now let's do what is the pH of a basic, a solution of a weak base. So in terms of weak bases, just a general equation. So we had HA for the general, for a weak acid. For a weak base, we could generally just call it B. We write it with water. For a weak base, you do want to write the water because the base is, what it means to be a base is it grabs a proton. And it needs to be able to grab a proton from somewhere. So it's grabbing it from the water. And so the proton's going to be coming from the water, and the base is going to act like a base. It's going to accept the proton. Okay, so the H2O has now lost an H, and the B is gained the H plus. So it's going to be now BH plus, gained an H, also gained a plus charge, went up by 1 unit right here, gained a plus charge. And the water lost an H, so now it has an oxygen, only 1 H. Also, it lost H plus, that's very important. So the charge went down by 1 unit from 0 down to -1. So that's how you generally write the equilibrium equation for a weak base, acting like a base. And the K for this equation is called the KB for the base. So in general, so we have, this is the base, water's acting like the acid, we get the conjugate acid of the base, we get the conjugate base of water. And the K for this reaction is called KB, the base dissociation constant. This is the K for a reaction where you have a base acting like a base and grabbing a proton. It's written the same way as any other K you would write. It's just for this specific type of reaction. So products go on top, each to the first power. So BH plus to the first power, hydroxide to the first power. And then the base goes on the bottom. Water is not included because it's not aqueous or gas. And the K for this reaction is called the KB of this base. And this is the equation, the way you'd write the equation for a base acting like a base. Grabs a proton from water. So a good example is ammonia. So that's our kind of quintessential example of a weak base. You probably talked about it a little bit in your previous classes too. I'll point out to you that basically all your weak bases, almost all of them you're going to see are either going to be negative ions or they will be neutral molecules that contain the atom nitrogen. So like NH3, because it's the nitrogen, the lone pair that actually bonds to the H plus here. So here we have the weak base ammonia. It's going to be an equilibrium. It's a weak base. It's not one of our 6 strong bases. Again, the H plus is going to go from the water to the ammonia. So it will now no longer have 3 H's. It will have 4. Also, the charge goes up by 1 unit from 0 up to +1. The water lost the H, so now there's not 2 H's anymore, there's only 1, and it lost H plus is what it lost, so the charge goes down by 1 from 0 down to -1. So if we were writing the KB for ammonia, it would be, again, just products over reactants for this particular equation. Ammonium ion and hydroxide ion on the top, each to the first power, and on the bottom, ammonia concentration to the first power, and we don't include water. So this expression is what the Kb is for ammonia. The expression for the Kb for ammonia. Any questions on writing the base equilibrium reaction?
No.
No? Anyone else? So if I say the Kb for this base is this, it means it's referring to the K for a reaction written in this way. Okay. So here are some Kb's for a variety of bases here. Notice again what they all have in common. They all have nitrogen ions somewhere. It's because it's nitrogen atoms rather. It's because it's a nitrogen atom that generally accepts the proton by using its lone pair to bond with the H+. So, and then we have the Ka's for the conjugate acid of the base. We're going to deal with soon with dealing with the Ka's and Kb's of ions. For now, we've only talked about neutral acids and neutral bases, but soon we will begin to talk about the conjugate acids of neutral acids. These are positive ions, and the conjugate bases of neutral acids, which are negative ions. So what you can see though is the stronger the base, the bigger the Kb for the base, the smaller the Ka for the conjugate acid. Makes a lot of sense, right? Because the stronger a base is, the more it wants to grab protons. That means it's a strong base. It really wants to grab and hang on to protons. Well, that means its conjugate acid, it does not want to release that proton. It wants to stay stuck with it. So you can see the stronger the base, the weaker the conjugate acid. We talked about this at the beginning. So the stronger the base here, the weaker the conjugate acid. We talked about this near the beginning of the chapter. I'm just reminding you guys. So here's a weaker base and it has a stronger conjugate acid, because the weaker the base, that means the less it wants to grab and hang on to protons. So its conjugate acid would release those protons easier. So let's do calculate the pH, but this time for a weak base solution. Okay, so we've got 0.4 molar of ammonia at 25 Celsius. The K is this. Remember, notice that we're always providing the temperature with the K, right? Remember, K's are temperature dependent. That's something to keep in mind from the last chapter. But it doesn't, the number is not used in the problem, 25 Celsius. But let's now start by writing the reaction. It's the same one as we saw on the last slide, so I'll just put it up here. Ammonia with water, acting like a base, grabbing a proton. It gets one more H, charge goes up by 1 right here. Water gives a proton, has one less H, charge goes down by 1 from 0 down to -1. Since we're solving for equilibrium concentrations, we need an ice table. Here's our ice table. Initially, we have 0.4 molar of ammonia. We've got none of the ammonium ion, and we've got about 0 of hydroxide. Now, we do know that even in pure water, there's 1 times 10 to the minus 14 molar of hydroxide ions. That is true, but we're hoping that it's small enough that it's not going to affect our calculation, and usually it is. So that's something you should always think about, but generally these questions are set up so that it will be negligible. Otherwise, the question would become much harder. Okay, so we know this reaction must go forward because Q is 0, which is less than K. This is because there are no products. So the reaction must go forward. It cannot go back. So we're going to put minus 1x, 1 because there's a 1 here. We don't write the 1 though. Plus 1x over here and plus 1x for the hydroxide. So our ammonia concentration is 0.4 minus x. Our ammonium concentration is x, and our hydroxide concentration is x. And so now we write the expression for the Kb. It is the products, NH4 plus and hydroxide over reactants, ammonium. And next we're going to plug in these concentrations. So make a note of these. Equilibrium concentration for NH4 plus and hydroxide are going to be X. We're going to plug these in right there. And for ammonium, it will be 0.4 minus, or ammonia rather, it will be 0.4 minus X, which will go here. And the KB is written right here. So KB is X times X over 0.4 minus X. Again, we're going to hope to use our simplifying assumption. So that 0.4 minus X is about the same as 0.4. We should do a pre-check. I didn't write it up here, but you should always do the pre-check. Often you can visually see it. So if I'm looking at this number, I can tell it's if I'm looking at the KB here rather, I can really tell that it's over 400 times smaller than this one. But if I want to just make extra sure, 0.4 divide by 1.8 e to the minus 5, and I get 22,000. So yes, this number 0.4 is 22,000 bigger than the K. So we are okay, at least for our pre-check, to use the simplifying assumption. All right, and so now we're going to solve. Let's multiply both sides by 0.4. Okay, so I'm going to draw here. So times 0.40 cancels here, times 0.40. So let's do that in the calculator now. It's going to be 0.4 times 1.8 e minus 5. And so we get, this is 7.2 times 10 to the minus 6, and the other side will be the x squared. So x squared equals 7.2 times 10 to the minus 6. Now we're going to square root both sides. Oh, you guys can see my writing? Yeah, okay. Yeah, okay, so square root both sides. So let's square root that number now. So it's going to be 7.2 times 10 to the minus 6, and we're going to do that to the 1/2 power, 0.5, and we get 2.7 times 10 to the minus 3 is X, or 0.0027 molar. Okay, so one extra step here for bases is that we get the hydroxide concentration instead of the hydronium concentration. So we have to figure out the hydronium concentration. Remember, the hydronium concentration will be the Kw divided by the hydroxide, because they always multiply to 1 times 10 to the minus 14. So we take this, we put it for the concentration of hydroxide, and we divide 1 times 10 to the minus 14, divide by 0.0027. And we get 3.7 times 10 to the minus 12. So that's our hydronium concentration. Now to get the pH, we just take the negative log of that. So negative log of 3.7 times 10 to the minus 12. So we have 3.7 times 10 to the minus 12. We're going to take the log and we'll change the sign. So we get 11.43. And remember, we write this with 2 after the decimal because our original data had 2 sig figs that we logged. So that's how you figure out the pH if you're given a concentration of a weak base. Anyone want me to go back to one of these steps here? Okay, I'm gonna, so in the lab, I'm gonna finish off lesson 18 and I'll give you a little preview of lesson 19, enough to kind of show you what the lab's going to be about. And then you'll use the software to actually visualize a titration curve for yourself. So this is a good lab. I generally have it. The lab actually usually is right at the beginning of chapter 19. So even though you haven't done any titration calculations yet, you're not really asked to. You're simply asked to observe what is the pH along the course of a titration. And so this should be pretty interesting for you. All right. So I will see you guys when we meet again in lab a little later to finish this off. Okay, I'll see you guys in a little bit.
I see you.
All right, see ya.